We will start atomic and nuclear physics from this lecture. So in this lecture, our objectives are that you will get familiar with the structure of atom, and then we will focus what is a nucleus. Of course, this is all nuclear physics. And then we will learn about proton number, nucleon number, and we will go through briefly about radioactive elements. Before we dive into the nucleus, let's start the story from the very beginning. So we can go back in time when the Rutherford did an experiment in 1911 because he wanted to know what is the fundamental unit of matter, because we know matter is made of something, right? He wanted to know the indivisible unit of matter. I mean, if we cut something into a smaller and smaller and smaller piece, we will finally arrive at a point where we cannot divide that smallest unit into more units. Then that will be the fundamental unit of matter. So in his experiment, he took a gold foil. You can see on the left side that yellowish piece, and I will help you to understand the experiment Rutherford did in 1911 with the help of this animation. So here is the gold foil, and then you can see a small part of this foil which is projected here, and then you can see that it is made of something, right? Because if you are back in time when the year was 1911, so it means you don't know anything what is inside. So you are just seeing a projected view of that gold foil, and then he hit this gold foil with alpha particles, and I will tell you later what are actually alpha particles. But according to his experiment, he knew that alpha particles are positively charged. And then he hit this gold foil with alpha particles, and then you will see the interaction of alpha particles with the gold foil in this magnified projected area, because then you can see what is happening inside, because these are his observations which he found in another way, but you will see it in this with the help of this animation. So I am starting the alpha particle gun, and then you can see that alpha particles are hitting the gold foil on the left, and then you can see a magnified view. And what Rutherford observed from this experiment, that a lot of alpha particles, they just went straight through the gold foil, and gold foil was ultra thin. So that because he wanted to know that what is the basic unit of this material, so he wanted to put it as thin as possible so that there are only a few units which the alpha particles will interact, and then because then he can find the information about those fundamental units. So you can see a lot of alpha particles, they just went through straight through the gold foil. But what he observed was that a small fraction of the alpha particles were deflected. So you can see that they are deflected at certain angles. Some are deflected at higher angles, some at lower angles, but they are deflected. And he knew that time that alpha particles were positively charged. So if you hit something from the source and then it is deflected, it means there is some positive charge, because we know that two positive charges repel each other from the Coulomb's repulsion. So he concluded that there is some positive charge and it is concentrated. It is not spread everywhere. That positive charge is concentrated. And then he observed one more thing, and that is very important, that although a small fraction were deflected at certain angles, but there was even a very small fraction, a tiny fraction of them, they just went back to the source. I mean, if an alpha particle is coming, Then after some interaction with something, it just went back where it came from. And the friction of those alpha particles were way small than the particles which were either deflected or went straight through the material. So he concluded two things from these two observations. First, that most of the mass of the atom is concentrated over a very small tiny spot, and that was nucleus. And second, because of these deflections, if I want to show you that interaction, here are alpha particles and this is the nucleus of an atom. So you see these deflections mean if something comes straight and then it goes back to the source, it means there is some mass, and fraction of those particles were very small, and because of that he concluded that almost all the mass of the atom is concentrated over a very small tiny volume. But from the other deflection, you see an alpha particle is coming and it is deflected. From this he concluded that that tiny mass has positive charge, because if you observe the interaction like that, what can you say about this interaction? Especially when you know that these alpha particles are positively charged, and now you see that they come and then they are deflected at different angles. Of course you will say that there is some positive charge here. That is why they are deflected, because two positively charged, they repel each other, and because of that repulsion they will behave like that. But if an alpha particle comes straight and then it goes back to the same way where it came from, then you will conclude that there was some mass, because it suggests there was some head-on collision with some mass. But if there is a deflection nearby something and then they are deflected at certain angles, then it suggests that is existence of some positive charge at that place, because when two charges repel they form different angles. But if there is a head-on collision, then the particle will just go back to the same way where it came from. So because of these two deflections, he found that he found the existence of some positive charge, and because of a very small fraction of the deflections that are especially the deflections of 180 degrees mean if after some certain interaction the alpha particle will go back to the source where it was coming from, and it suggests that the existence of mass, and because most of them just passed straight through the material, it means most of the atom or the fundamental unit is empty. So in this way, the Rutherford is credited to discover the protons in the nucleus of the atoms in 1917. Electron was already discovered by J.J. Thomson in 1897, and then James Chadwick discovered neutron in 1932, and then there had been a lot of developments and discoveries. So now we have the image of the atom, a classical image of the atom, that almost all the mass of the atom is concentrated over a very small volume which is called nucleus, and we know that in the nucleus there are protons and neutrons. And electrons, they orbits the nucleus around the electrons, they orbits the nucleus in circular orbits, and that's why we say that most of the atom is empty, because most of the mass is concentrated over a very small tiny spot at the center of a classical model of the atom like this. So let's make an atom and explore the relevant quantities. So I will put one proton in the nucleus. Oh, and it says that it's hydrogen atom, the first element in the periodic table. We know that periodic elements are listed in the periodic table according to a specific order. And what is that order? You will see it later. So it means if I put one proton in the nucleus, it is hydrogen. So don't you think that this is how we arrange number of elements in the periodic table? By number of protons. And I can see that mass number is 1 and it says that it is hydrogen ion because we know that usually the atom is neutral, mean there is no net charge in the atom for most of the atoms. Or if there are the number of positive and negative charges are equal, that is of course it's the same because then net charge is 0. So let me make it a neutral atom. So I pick one electron and I know that it will go into the first orbit. Now it is a hydrogen atom, neutral atom, mass number is still 1. Why? Because I know electrons have some masses, but it is not adding something. It is saying that mass number is 1. And it seems that mass number only cares about number of protons in the nucleus and it doesn't care about number of electrons in the orbits around the nucleus. So that is true. But this is not a complete picture. I will tell you later. Now you see that the net charge is 0. When there is no electron, you see that there is some charge. It is showing +1 because there is one proton in the nucleus and there is no negative charge to balance that charge. So when I add one electron into the first orbit, it is hydrogen. So this is how we identify atoms. We identify atoms or elements according to number of protons in the nucleus. We don't care about electrons in the orbits. That is why this number of protons in the nucleus we represent it with Z and we call it is proton number. This is proton number. Proton number tells us the number of protons in the nucleus and this is the way we arrange elements in the periodic table. For example, if I add one more proton, so the next element is helium in the periodic table. So the first, if there is one proton in the nucleus, it is hydrogen. If I put one more proton into the nucleus, two protons, it should be helium, right? Because the atomic number of helium is 2, which shows that there should be two protons in the nucleus. So let me add one proton in the, yes, it says that this is helium ion, of course, because charges are not balanced, but it is unstable. Okay, why it is unstable and what should I do to stabilize this atom? Let me add one neutron. Oh wow, now it is stable and I can add one more neutron. It's still stable and it is still helium. It means that it doesn't matter. It means the function of neutrons is to stabilize the atom so that the atom is stable and they don't have much more role in identification of the element because you see I am adding neutrons, I am adding neutrons, I am adding, although it is not stable but it is still helium. So it means identification of the element is only through number of protons in the nucleus. So let me take these extra neutrons because this is not a stable atom. It means this atom does not exist in nature. So now this is helium. What if I add one more electron? Okay, so it is still a stable helium atom. And now it is neutral, of course, because there are two electrons and two protons in the nucleus. Mass number is 4, which means the sum of protons and neutrons is 4. So mass number is the sum of protons and neutrons in the nucleus. Number of protons is atomic number. This is how these elements are arranged. As the number of protons increases in the nucleus, these atoms are arranged according to these rows from left to right. That is not very strict arrangement, but this is a general way how the atoms are arranged in the periodic table. So this is helium, neutral helium atom. So the number of protons in the nucleus is proton number. We represent it with Z. Number of neutrons in the nucleus, we call it neutron number. And mass number is the sum of number of protons or the proton number and neutron number. So of course there are two protons and two neutrons, so mass number is 4. So now if I take one neutron and one proton and of course one neutron, it is still hydrogen. Of course I told you that number of electrons will not change the nature of this atom. So This is the actual neutral stable hydrogen atom. A hydrogen atom has one proton in the nucleus and one electron in the first orbit. That's all. This is a complete hydrogen atom. But so this proton is mass number is 1, proton number is 1, neutron number is 0, of course, because there is no neutron. This is the way we represent atoms, and because we are studying nuclear physics, so we will only focus with at the nucleus. We don't care about electrons. So now I want you to observe one more thing. When I add one neutron, it is a still stable hydrogen neutral atom, because we know neutrons have no charge. But then what is the difference? If there is no neutron, it is still hydrogen. If I add one neutron, it is still hydrogen. If I add one more neutron, it is unstable, but it says it is still hydrogen. So how to differentiate it? So this one is the natural or neutral hydrogen atom, and when I add one neutron, it is isotope of hydrogen, and we call it deuterium. Deuterium is hydrogen but with one extra neutron. And similarly, if I add one more neutron into the nucleus of this hydrogen, it is unstable, but it is still hydrogen. It is showing that it is still hydrogen. So this is also an isotope of hydrogen. This is, we call them isotopes. Isotopes are the same elements but with different number of neutrons. And we call this isotope, which is showing as unstable, but it exists in, and we call it tritium. If I take one neutron, it is deuterium. If I take one more, of course, neutron from the nucleus, now this is neutral atom hydrogen. And if the number of protons if the number of neutrons are different in the nucleus, it is still the same element, because we identify elements with number of protons in the nucleus and not with the number of neutrons. Of course, neutrons add mass to the atom, so that's why when we want to calculate the mass of the atom, we don't care about mass of electrons, because this mass is useless for us. It is spread over a larger volume, and they are away. Most of the volume is concentrated into very tiny spot at the center of this classical model of the atom. So this is actually the mass. We can ignore masses of electrons around the orbits. So the one point that we identify number of elements with number of protons. So if I take this one electron, it is hydrogen ion. Ion means that there is imbalance of charge, because there is one proton but there is no electron to balance this charge. It is still stable. It is hydrogen, but it is hydrogen ion. If I add one more proton, now you see it is helium, and helium is unstable. So this is the function of neutrons. They stabilize the atoms. So this is helium, you see. So as you can see, mass number is 4, of course, because proton number is 2, neutron number is 2, number of protons and number of neutrons in the nucleus, and sum of 2 plus 2 is 4. So mass number is the sum of proton and neutron numbers. And we call these both of these particles in the nucleus as nucleons. So if I want to tell you that how many protons and neutrons are there in the nucleus, I can say how many nucleons are there, and you will understand that I am talking about both protons and neutrons, or whatever present in the nucleus. Of course, only these two particles will be present in the nucleus. So this is helium, because number of protons are 2. So this is how we arrange elements in the periodic table. The next is lithium. So if I add one more proton, this is now lithium. Of course, it is not stable. I can add more neutrons to stabilize this one, but it is still lithium. If I add one more proton, now it should be beryllium. You see the next element. So you can get the trend in the periodic table, that this is how we identify elements in the periodic table with their number of protons in the nucleus. And neutrons are there only to stabilize the atom. So this is neutral hydrogen, and the number of neutrons have no role in the identification of the element, but they add mass to the atom. So mass of the atom is the mass of protons and neutrons in the nucleus, and we ignore masses of the electrons because they are not very useful. Their mass of an electron is less than mass of proton and neutron, and because they are away, they are spread over a larger volume, so that mass is not very useful for us, at least in the when we are studying the nuclear physics. So we will focus only in the nucleus, and now you know the relevant quantities, so we can move further to the next sections. So that animation was a bit random, so let's talk in more detail. So the atomic number, which is usually represented with Z, is number of protons in the nucleus, and this is the identification of the element. So if the number of protons in the nucleus is 1, it is hydrogen. If the number of protons in the nucleus is 2, it is helium, and this is how you identify. So this is Z, number of protons in the nucleus. Next is neutron number. And you know that neutron number is represented with N, and this is the number of neutrons in the nucleus. And the next is mass number. We represent it with A, and it is the sum of atomic number or proton number plus neutron number, because it shows it quantify the mass of an atom, because we don't add mass of electrons into the total mass of an atom. And the reason is that first, the most of the mass, which is mass of protons and neutrons, is concentrated over a very small volume at the center of the atom, and electrons, they are spread over a larger volume, so that mass is not very useful in most of the situations. Secondly, the mass of electron is less than mass of proton and mass of neutron. So here I have given the masses of these particles. So you see the mass of electron is this. So because the numbers are given in scientific notation, so you may not feel like how large or how small is their masses are. So let me give you an example. So let's calculate the ratio of mass of proton divided by mass of an electron, because this ratio will give you the idea that how small is the mass of an electron, because it's not easy to guess it from these numbers. So I am going to calculate the ratio of mass of proton, which is here 1.672, and then 623, and then 10 to the power of negative 27 kilograms. Then I will write mass of electron, which is here 9.109 and 390 multiplied by 10 to the power negative 31 kilogram. And my calculator tells me that this value is 1836, and I am ignoring the fractional part. So it means that mass of proton is 1836 times the mass of electron. So you see, mass of an electron. So the mass of proton is way larger than mass of an electron. It is more than 1000 times the mass of electron, or if I say roughly speaking, it is about 2000 times the mass of an electron. So this mass of proton is too much. And then because it is concentrated over a very tiny small volume, but electrons, they are orbiting around the nucleus over a larger volume and they are separated from each other. So we don't count mass of electrons when we are referring to an element or atom. When if I ask you calculate the mass of the hydrogen atom, so you know there is only one proton in the nucleus of the hydrogen. I don't care about number of electrons around the orbits because identification of the element is always with the number of protons, mean the Z number in the nucleus. So if I ask you what is the mass of hydrogen atom, it's easy. You see there is only one proton in the nucleus. So you just say mass of the hydrogen atom is 1.672623 10 to the power negative 27 kilogram, because mass of proton is actually mass of the hydrogen because there is only one proton available in the hydrogen atom. But remember, I am talking only about the stable neutral hydrogen atom, not the isotopes. Remember that. If I asked you to calculate the mass of deuterium, deuterium is isotope of hydrogen, and the only difference with this hydrogen and deuterium is that deuterium has one extra neutron. So in the deuterium nucleus, there is one proton plus one neutron. Neutron has no charge, so there is no problem. This is the nucleus of deuterium. It is still hydrogen, but we call it isotope of hydrogen because in the first case there was no neutron, there was only one proton, but now there is one neutron. So number of neutrons in the nuclei are different. That is why it is the same element, but something is different. Number of protons are different in the nuclei. So we have to distinguish them. I cannot say this is hydrogen, this is hydrogen. So I have to give it another name. So another name is deuterium. It is deuterium. It is still hydrogen, but with one extra neutron in the nucleus. But in the first case, there was no neutron. It was only one proton and one electron in the orbit, and we don't care about number of electrons in the orbits because we don't count them when we are calculating the masses, and we are studying nuclear physics, so we are only concerned with the nucleus. So if I asked you what is the mass of the deuterium, so of course you will add the mass of proton plus mass of neutron and add them up, give me the final value. That is the mass of deuterium, you see. And what is the mass number? Mass number A is 2 because mass number is only the proton number plus neutron number. There is one proton and one neutron. So 1 plus 1 equals 2. So mass number is 2. But if I ask to tell me the mass of the atom, then you have to calculate the relevant masses of protons and neutrons and if they are available in how much quantity. So it's easy, right? You can calculate the mass if you know the individual masses of proton and neutron. Rest is just simple calculation. So when I want to write some element, for example here, so I need to give you this information. The mass number and proton number are Z, because these two are very important quantities when we are studying the nucleus of an atom. So how will I give you the number? So let's decide. So I will write A at top of the symbol of the element. So whatever is the symbol, I will write the symbol and then I will write the mass number here and Z number here. By the way, just remember different textbooks, they use different notations. So I'm just using one notation that whenever I want to give you an element with the information about the nucleus, so I will give mass number at the top of the symbol, and then below I will write the proton number. So you know that this is proton number and this is mass number. And don't forget, mass number is the sum of number Z plus N. So N is number of neutrons present in the nucleus and Z is number of protons present in the nucleus. So for example, for the hydrogen, I will write H, 1 and 1. So now you know at the top it is actually the mass number. It means the sum of number of protons and neutrons in the nucleus of the hydrogen is 1, and we know that there is only one proton in the nucleus of the hydrogen. There is no proton, so 1 plus 0 equals 1. So this is A. We call it mass number, and Z is equal to number of protons in the nucleus, which is 1, so it is 1. The purpose of giving these two numbers is because when you have these two numbers, you can always find number of neutrons in the nucleus, because there is no neutron in the nucleus of hydrogen atom, so they are same. So if the mass number and Z number, they are same, it means there are no neutrons in the nucleus. But when they are different, uh, for example, aluminum, it is also an element in the periodic table. So according to this definition, if I give you the numbers, I will write 27, 13. So now tell me, what are the number of protons and neutrons in the nucleus of aluminum? Can you tell me? I have given you all the necessary detail according to our agreed format that I will write mass number at the upper left corner, and then in the lower left corner I will write proton number. So answer is very easy. Number of protons in the nucleus of aluminum is 13. There are 13 protons in the nucleus of aluminum. So how can I find number of neutrons in the nucleus of aluminum? How can I find that? You know that the mass number is actually the sum of proton and neutron number, that is equal to 27. And now you know what is Z, number of protons. We represent it with Z, and number of neutron we represent it with N. So if you know Z, you can find N, because N is the difference of mass number minus Z number. And we know that 27 minus Z number is 13. So there are 14 neutrons in the nucleus of aluminum. Is it easy, right? I hope you can solve relevant problems of your textbook very easily if you know the concept of mass number and proton number, or Z. Now it's time to solve this problem. Here I have two unknown elements. So I have represented both of them as X. And as you know that according to our agreed format, I wrote mass numbers here and Z numbers are the proton numbers here. Or we also call them atomic numbers. So atomic numbers are given there. These are two unknown elements, and please tell me what are these elements and tell me number of protons and number of neutrons in their nuclei. So solve it. As we know that we can find what is that element only with atomic number Z or proton number Z, because this number will tell us what is that element, and once I know this number I can find the element. So let me find it is Z. If it is Z, number of protons in the nucleus, because I can write number of protons is 13, and number of protons for the second element, whatever it is also 13. So it means it is same element, because if number of protons are same, it is same element, right? So now all we need to do is to see the periodic table and find this 13 number, because we know the number of elements are arranged according to the atomic number or number of protons and their nuclei. So number of protons are 3. Let me use my animations to find what is that element. So here I have protons, so I am adding protons. One proton is, if there is one proton, it is hydrogen, so I will add one more. Now it is helium, so you see in the periodic table it is moving forward. Now I add third one, it is lithium. If there are 4 protons, it is beryllium. And now I am not adding relevant electrons. I don't care about them because all I want to know is the name of the element, and name of the element only matters with number of protons. So I will not add any, I will add only protons. So if there are 5 protons, now it is boron, you see, it is moving next. And then if there are 6, now we have this. So if I keep going, and I am not adding any neutrons as well because all I want to know is the name of the element, and name I can find name of the element. So now I have added 10 protons because the mass number is showing 10 because there are no neutrons. So this mass number is equal to Z. So unfortunately, I cannot add more protons to see like what will come at 13. But from the trend, I know that if 1 hydrogen, then 2 helium, 3, 4, 5, 6, 7, 8, 9, 10. So I can keep going like that. 11, 12, 13. Okay, 13 is aluminum in the periodic table. I can see that. So, okay, I found it. It is aluminum. It is aluminum. Even if you can see a periodic table, and I can see that on 13, it is aluminum. You see in the periodic table. So, you can consult periodic table to find what is that element. So, I found it is aluminum. So, the element is aluminum, and the second is also aluminum. But what is the difference? Let's go to the mass number and find the number of neutrons. So number of neutrons in the first case of aluminum, it should be 26. So I can subtract number of protons from 26 to give me the number of protons. So I am using my calculator. 26 minus 13. Okay, number of neutrons are also 13. They are equal. This is also aluminum. So let's see what is the difference with this one. Because I know it is also aluminum. Number of protons are same. It is aluminum. But let's see. Number of neutrons in the second case. So number of neutrons 27 minus 13, and it is 14. Okay. So although it is aluminum, but number of neutrons are different. In the first case of aluminum, number of neutrons are 13. In the second case of aluminum, number of neutrons are 14. So what information can you get from this data? These are isotopes. This is aluminum and this is its isotopes. This is its isotope because number of protons are different. Here 13, here 14. They are same element, but because the number of neutrons in their nuclei are different, they are isotopes. So at the beginning, I said that the Rutherford used alpha particles to hit a gold foil to find the information about the atoms. So what are alpha particles? So alpha particles are actually helium nuclei. So you know helium is the second element in the periodic table. Second means there should be 2 protons in the nucleus. And because it is helium, so there should be 2 neutrons. This is helium ion because there are no electrons in the orbits to balance the charge of protons. So this is helium ion. And this is alpha particle. An alpha particle is helium nuclei. It means it has only nucleus. It has no orbits because there are no electrons, so no orbits, nothing. It has only this central part, these 4 particles together. These are alpha particles. And Rutherford, he targeted the gold foil with these helium nuclei. I mean only the nucleus, no more electrons. Now what is radioactivity? We have studied the nucleus of atoms. So in the nucleus there are protons and neutrons and they are combined, and all the mass of the atom is concentrated into a very small volume. And here I have shown just a typical nucleus of certain atom. So sometimes it happens, you have seen in the animation that sometimes atom is not stable. I mean number of protons and neutrons. So they have to be in certain numbers and certain quantities in certain setups so that the atom is stable. It will remain there. I mean, this setup will stay like this, but sometimes it doesn't happen. You saw it when I was adding number of protons and neutrons. So sometimes atom gets unstable. So if an atom is unstable, then of course it means its nucleus is not stable. This setup is not in its optimum situation. So sometimes it happens that an unstable nucleus, it is unstable. So as a result of this instability, give it will emit some radiation to become stable. And that radiation, suppose it can take out some certain radiation. And if you want to see the number of, for example, it emits this radiation, it will get out of the nucleus because nucleus is unstable, and it will emit certain radiation. If you know, I just told you that this is actually alpha radiation. Alpha radiation is helium nuclei. Helium has two protons and two neutrons in the nucleus, and it has and alpha particles are helium nuclei. I mean, it has no electrons, only two protons and two neutrons. It is just a nucleus. So when an unstable nucleus which has a large number of protons and neutrons, so it can happen that it is unstable somehow, and it emits certain radiation, maybe alpha particles. So when alpha particles come out of the nucleus, now the nucleus is stable and alpha particles are out, alpha radiation is out. But something will happen. I told you that number of protons or atomic number decides what is the element. So whatever element it was before emitting the radiation, now number of protons is reduced, and of course number of neutrons as well. So now this element, whatever was the number of protons and neutrons before, so now the number of protons are less than are lesser by a quantity 2, because 2 protons are out of the nucleus. So you can see in the periodic table that, for example, if the element is whatever aluminum, and if somehow you take two protons out of aluminum, it will become, because now number of protons are 13, and if you subtract two protons it will become 11. So it will not be aluminum anymore, it will become sodium. So if you take two protons out of the nucleus of aluminum, it will become sodium. Its mass is reduced and everything is different. So the disintegration of the nucleus as a result of emission of certain radiation, alpha, there are two other radiations, beta and gamma. Then as the result of this the result of this disintegration of the nucleus or an unstable nucleus, then this nucleus, whatever element it was, it will change into another lower atomic level element. As an example, you saw that aluminum was at a higher atomic number 13, but then it will become sodium, which is at lower atomic number, because of course number of protons are reduced. This phenomenon is called radioactivity. If it happens naturally, it is natural radioactivity. We can make it happen artificially, that is called artificial radioactivity. This is radioactivity. Some elements, their nucleus disintegrates by emitting certain radiation. That radiation, of course, takes away some number of protons or neutrons, and as a result, that element changes into another element with a lower atomic number. So this, and we will get this radiation out of the nucleus. This phenomenon is radioactivity. This type of disintegration of a nucleus, when it emits a helium nuclei, of course it reduces the atomic number by 2 and mass number by 4. Such type of radioactivity is called alpha decay. There are beta decay, gamma decay, and certain reactions.